Welcome back, Algebra 2. Today we are continuing polynomial functions, and we're actually going to be graphing polynomial functions today. I will also be teaching you how to use Desmos to graph them. So for today, our learning targets are, I want to make sure that you guys can identify the key features of a polynomial function, such as end behavior, turning points, maximum and minimums, and increasing and decreasing intervals. I also want to make sure you guys know how to use Desmos to find the turning points of a polynomial function. So as a reminder, as we're looking at polynomials, we have the standard form, which says that a n x to the n, and you have all this gibberish here, but really what this means is you have a coefficient and the highest exponent, and then you have a different coefficient and an exponent that is one lower, and then another different coefficient. The exponents keep going down. Suddenly we get to a coefficient with our x term that is to a power of 1, and then we just have our constant. See how there is no variable tied to it. So some notes that we need to remember is all coefficients must be real numbers. So that means that we will not have imaginary numbers as part of our polynomials. We may have them as part of our solutions, but we do not have them as part of the actual polynomial. So another thing to remember is all exponents are whole numbers. This is really just for polynomial functions, so we don't want to see any fractional exponents. We also don't want to see any negatives in our polynomial. We also say that our very first coefficient cannot be 0. That kind of makes sense because you wouldn't have, if this was x to the 5th, but you put a 0 in front of it, it's not really a 5th degree polynomial. It's going to be less than that. And then lastly, we have our degree is the highest exponent of the polynomial. So again, if this is x to the 5th, then our degree is 5. I'm going to scroll down a little, and now we're going to look at the base shapes of our polynomials. So when I say the base shapes, this means that it is just that degree and there are no other terms. So for a degree of 0, which would look something like f of x equals any number, so if we picked something like 5, then our graph is just going to be a horizontal line. I'm going to do my best to draw a horizontal line. We have our line here, we have the arrow on the other side. So it is just a horizontal line if the degree is 0. We also know this as a constant polynomial. Then we get into degree of 1. So this could be anything like f of x equals x, or 2x, or 3x. But again, we're not adding anything to it. We're just saying that it's basically at its base level. So our linear polynomial looks something like this. Again, I know it's not perfect. It is a little difficult to draw on this. So that's a linear polynomial. Then degree 2. So if our polynomial has a degree of 2, that makes it a quadratic polynomial. We've dealt with these. This was all last unit. So as we're bringing the mouse over, you're going to see that I'm going to try and draw the best parabola I can. Going to look a little wobbly. I haven't figured out the this board yet, but it makes a parabola. So if we wanted to know what this function was, it is f of x equals x squared. So notice how we are not adding x or our constant or anything. These are just the base forms of the graph. I'm going to scroll down. Then we have degree 3, which is a cubic polynomial. So if we're thinking about what this parent function is, we have f of x equals x cubed. So we have x cubed, and if we're looking at the graph, it's going to start down here, going to kind of work its way towards 0. It's coming back up. We have our cubic polynomial. So then, realistically, we have all even degrees that are larger than 0. And in this example, I'm actually going to use one that is larger than 2. But all degrees that are larger than 0 in their base form look like a parabola. I specifically made this one a little thinner than our first one, just because if we're saying that this is f of x equals x to the 4th or x to the 6th, it is actually going to be a bit steeper than our degree 2. So that's why it looks thinner, because it's actually being steeper. So we're pulling it up a little bit. But that makes sense if you think about it. If you plug in 1, you're going to get 1. But if you plug in 2, suddenly 2 to the 4th is way bigger than 2 squared. Because 2 squared is 4, and 2 to the 4th is 16. So it's going to rise much more quickly. And odd degrees is kind of the same thing. The reason I said larger than 1 is because if you'll notice, our linear polynomial does go from the bottom left to the top right, and so does our cubic, but our cubic has a little bit of a curve, and most of the odd degrees besides 1 have a little bit of a curve. So again, I'm going to kind of write this where we come up to the 0, and then we come back up. I tried to make this a bit more steep than our degree 3. I got a little lopsided on the right side. But any odd degree looks like this, at least in its base form. So in the base, if we have f of x equals x to the 5th, it looks like this. They start getting a little crazy when we start adding other terms to them. So if this was x 5th plus x to the 4th minus 3x squared or something crazy like that, it will begin to change shape. This is just the shape in its most basic form. So, some of the features that we need to know about a polynomial function. We need to know the turning point, which is the point on a graph where it changes direction. That kind of makes sense. You know, it's the point that it's turning. So this is the point where it changes direction. Then at the turning points, we have a relative maximum so that is when the turning point is at the top of the curve. And we have a relative minimum when the turning point is at the, I'm sure you guessed it, bottom of the curve. So let me just fix that M there a little bit. Bottom of the curve. Then we also have an absolute maximum and an absolute minimum. I do want to warn you about this, is we may not have any maximums or minimums at all in the graph, but sometimes we will, and we're looking for either relative or absolute. So the absolute maximum is the absolute highest part of the graph. Right? Like you guys probably already knew that, but we're just writing it down to make sure you have these definitions. So, if our absolute maximum is the absolute highest part of the graph, our absolute minimum is the absolute lowest part of the graph. the absolute lowest part of the graph. These maximums and minimums are actually, they have a specific name. We call them I've heard this pronounced a couple ways. I usually pronounce it as extrema or extrema, but I think it's extrema, which basically means all of the maximums or the minimums of the graph. So we may call these local, which is the relative ones, or global, which is the absolute maximums or minimums. Next, we have the increasing intervals, and you'll never guess what these are doing. These are all the intervals in which the graph is increasing. So, that was a real hard one. Decreasing, just as hard. The decreasing intervals are all the intervals in which the graph is decreasing. I'm sure all of your minds are completely blown right now. So next, I want to have a quick note that the max number of zeros so the x-intercepts is n, where n is the degree of the polynomial. All this means is if we have a degree of 3, then the max number of zeros that we can have is 3. It doesn't guarantee that we're going to have 3. It just says that that is the max number of zeros that we can have. The max number of turning points, however, is n minus 1, where n is the degree of the polynomial. So again, looking at our example of n equals 3, our turning points that we could have a max of 2. This doesn't guarantee that we'll have 2. We could have 1. We could also have 0. But for this case, we can have a max of 2. So our next thing is we need to go to Desmos, because some of these functions are really hard to graph by ourselves unless we can factor them perfectly, which isn't always easy. So what I want you to do is you're going to go to desmos.com/calculator. We've used this before, but we're going to continue to use it. You're going to enter the polynomial function, and the way you do exponents is you're going to hit the shift key on your keyboard and the caret, which is right above the 6, and then Desmos will automatically label the turning points for you. It's great. So let me quickly switch over here. So here we are on Desmos, and what I'm going to type in is I need to say x, then we're going to hit shift 6 cubed. I'm going to hit the right arrow so it moves back down, minus 5x squared plus 4x minus 3. So as you can see here, it gives us a graph and it labels a few important points. It gives us the y-intercept, it gives us the x-intercept, and it also labels all of our turning points. So our turning points for this one, you can tell right away that they are not going to be very nice. That's the nice thing about Desmos, is we can still use these. So let's get back to the other sheet. I'll leave this up, but let's go back. We have so we want to come back to here, and instead of drawing the graph out, I'm going to just put that one up. So if we are looking at all of our important points of this graph, first we need to figure out domain and range. Our domain, it goes to the left forever, and it also goes to the right forever. So our domain with this function is going to be all real numbers. If you remember, we have our special R symbol for that, which is all real numbers. And our range, it extends downwards forever, and it extends upwards forever. So our range is also all real numbers. Then our increasing intervals, we're going to round all of these to 2 decimals, but as you can see, it extends from negative infinity to positive 0.46. So negative infinity to 0.46, or it's also increasing from 2.87, so 2.87 to positive infinity. Remember, with increasing and decreasing intervals, we are always just going to put parentheses around them. We never put brackets. Our decreasing intervals goes from 0.46 to 2.87. We have our increasing intervals. There are 2 of them because it's going up twice, and then it is going down in the middle. So our relative maximums, those are our points that are labeled. So our relative maximum is 0.46, comma, negative 2.12. So that's our maximum because it's at the top of the curve, and our relative minimum is 2.87, comma, negative 9.06. So that's our turning points for the graph. And then as x approaches infinity, so as x goes to the right forever and ever, we want to know what our y value is going to be. So as x moves to the right, y goes up and continues increasing, which means as x goes to infinity, our f of x, which is y, also goes to infinity. But as x moves to the left of that graph, we can see that it's heading down forever. So as x approaches negative infinity, y, or f of x, also approaches negative infinity. So that's this graph. And then I'm going to quickly take that off, and we're going to scroll down. So our second graph, I'm just going to pull it up real quick, and we have negative 1/4 x to the 4th plus 2x squared. So if I put that up, that is this graph. So let me move it just a hair. We can kind of take a closer look. I'm going to click on the turning points right here and here. So we have negative 2, 4 and positive 2, 4. But don't forget, we also have this turning point right here down at the bottom. This also is one of the x-intercepts, but it is a turning point as well. So with this one, our domain, our x is going to the left forever, and it's going to the right forever. So our domain is all real numbers. But with our range, you guys can see that it goes no higher than y equals 4. So the way we're going to write that is we're going to say y is less than or equal to 4. Or we can write it in interval notation. So this would be negative infinity to 4. And this time, since 4 is included, we can write the bracket. The only time we cannot write the bracket is for increasing and decreasing intervals. So this one has an increasing interval of negative infinity to negative 2. That's where it's increasing. It's also increasing. We can say that it is 0 to 2. It is also increasing from 0 to 2. So our decreasing intervals are from -2 to 0, because it's going down, or it's also decreasing from 2 to positive infinity. Remember that all of these are x values. So even though it is going down, the x is moving to the right, so it is still positive infinity. So our relative maximums, we actually do have 2 this time. We have -2, 4, and +2, 4. Those are both of our relative maximums. In this case, they are actually our absolute maximums because they are the highest point of the graph. And our relative minimums, we have 0, 0. And then for our end behavior, we can see that as x goes to infinity, so as x moves to the right, y is going to negative infinity, because f of x is really just y. And as x goes to the left, or negative infinity, f of x also goes to negative infinity. So both sides are moving downwards. We're going to go ahead and take that graph off the screen. Scroll down till we get to the next page. Now we are talking about end behavior of a graph. So first, we need to know the leading coefficient and we need to know the degree. So if our degree is even and our leading coefficient is positive, then we are going to have a graph that looks like this at the end. It's going to go up and to the left, and it's also going to go up and to the right. So then what if we have a negative leading coefficient, but our degree is still even? Well, then we are going to go down and to the left, and down and to the right. So we can kind of see this from our previous problem where we had a negative even degree and both sides went down. Now, if we have an odd degree, as x goes to the left, then our y is going to go down, and as x goes to the right or goes to positive infinity, our y is going to go up. So down to the left, up and to the right. Now, if we flip them for our even degrees, I would say that we're probably going to flip them for our odd degrees. So now with our odd degrees, we're going to go up and to the left, and we're going to go down and to the right. So the positive and negative just flip the signs, and the even tells us both are going the same direction, and the odd are going opposite directions. This will kind of make more sense as you just look at more polynomial functions. So for practice, we're going to decide whether the degree is even or odd if the leading coefficient is positive or negative, and we're going to draw arrows for the end behavior. So this one, the degree is 3, and this is in standard form. So we have a degree of 3, which is odd. And our leading coefficient, so that's this 4 here. So our leading coefficient is 4. That's positive. We have a positive coefficient. That tells us, so I will scroll right back up again. Our end behavior is going to be an odd and positive. So we expect it to go down and to the left and up and to the right. We don't know what happens in the middle. It could, curve down and come back up. It could just have one curve. It may have 2 turning points. we're not really sure, but we know what the end behavior is just by looking at it. So our next one, we have a degree of 6, and it is even. And our leading coefficient is this number right here. So -1/7, which is negative. If you remember from our notes at the top, it just said no negative exponents. Having negative coefficients and fractional coefficients is fine. So now that this one is even and it's negative, we expect to see it going down and to the left and down and to the right. If you want to pause and take a look at number 3, now that you're back, we're going to again look at the degree, which is 5. So our degree is 5. That is an odd degree. And our leading coefficient is -2. So this is negative. So our end behavior, again, we're going to look at the graph and decide that a negative odd degree goes up and to the left and down and to the right. So again, anything could happen in between these points. We could have a couple of turning points. We may just have one. But we know what the end behavior is just by looking at it. So now I really do want you to pause, and I want you to go ahead and try all 3 of these problems. So if you're looking at these, I want you to check what's true for number 4. I want you to check what's true for number 5, so odd, even, positive, negative. And then for number 6 and number 7, we are going to do x approaches negative infinity, y approaches infinity, and as x approaches positive infinity, y, or f of x, approaches negative infinity. And number 7 is the same way. So as x goes to the left, y goes up. As x goes to the right, y goes up. So go ahead and check off everything that you think is true. I'm going to give a second for you to pause. Okay, now that you're back, immediately I see that this is going the same direction. So I know that it is going to be even. I also know that it is going down, and normally I expect even ones to go up, so I'm going to say that this is a negative even polynomial. So it has an even degree and a negative coefficient. So then our second graph, it has 2 different directions, so I'm pretty sure the degree is going to be odd, and it starts from the left going down, and then the right is going up. So I think that this one is positive, because that is what a positive odd polynomial looks like. And then the functions that match the end behavior, if negative infinity, y goes to positive infinity, so that would basically mean it's going up and to the left, and then down and to the right. I'm thinking we have a negative coefficient and an odd polynomial. So that's this one. This one is odd, but the leading coefficient is positive, so it's not that. This one has an even degree, so it's not that. But this one is negative with an odd degree. So I would say those are the 2 functions that match this end behavior. And number 7, I would say we're going to the left and we're going up. We're going to the right and we're going up. So both directions are the same. So immediately I'm looking for an even degree. And then since they are going up, they are going to be a positive coefficient. So our only positive coefficient that has an even degree is this one. Hopefully you found this video helpful, and I will see you in the next one.